All right. Hopefully that's going. Okay, so now we checked homework. Let's jump into naive set theory. Why am I calling it naive set theory? It's not proper set theory. We're not going to do the full axiomatic development of set theory. We're going to do the fast and loose, just trying to quickly give you intuition for everything version of set theory. And it should be a really fast lecture. And then we can spend most of the time, hopefully, on some of your homework problems that you have coming up. All right, so first off, some basic definitions and relations with the set. What is a set? Intuitively, a set is an unordered, unique collection. It's unordered, it's unique, and it's collection. It has those three properties. It's an unordered, unique collection. I probably shouldn't have that comma there. Okay, notation. We use these curly braces to represent when we're starting and terminating a set, and then we comma separate the elements that are in the set. So this is a set containing 1, 2, and 3. Now, up here we said it's a unique collection, which means that adding duplicates doesn't matter. So the set 1, 2, 3 is the exact same thing as the set 1, 1, 2, 3. This is a set containing 3 elements, 1, 2, and 3, and that's all that's in there.
Okay, so you don't duplicate.
This set and this set are the exact same set.
So you can have 1, 1, 1, 1, 1, 1.
You could have 10,000 ones in there, a 2 and a 3, and it would still be a set with 3 items in it. 1, 2, and 3. Duplicates don't matter, that's what we mean by unique. And then order doesn't matter. So the set 1, 2, 3 is identical with the set 3, 2, 1. The order that you write them doesn't matter. Duplicates don't matter. So it's an unordered, unique collection. That's what we mean by that. As opposed to, you've probably seen lists. We use a list with 2 elements in it, often called an ordered pair, when we want to talk about something like a point. So the list 1, 2 is not the same thing as the list 1, 1, 2 is not the same thing as list 2, 1. The point 1, 2 on the xy plane, we go 1, 2, that's up here, is very different from the point 2, 1. And the point 1, 1, 2, well, that's a point now in 3-dimensional space. It's not even on the whiteboard. So when we use these parentheses like this for our collections, then order matters and duplicates matter. With sets, they don't. We're focusing on sets, not lists. With me?
Yes.
All right, next. So our first relation is a member of relation. X is a member of A, is how you read that, or X is in A. It says X is a member of A or X is in A. We're saying X is in A. A is a set here. This is something that is either always true or false. X is in A, we can always call that true or false. So it's a relation that takes 2 things.
So what exactly is like the little ED?
That's the epsilon symbol. That means is a member of, or in is how we typically read that. X in A. Examples. 1 is in the set containing 1, 2, and 3. The set containing 2 is in the set containing the set containing 1 and the set containing 2 and 3. That is one of the things listed out in this set. It's right there.
Right.
The set containing 1 is not in the set containing 1, 2, and 3. That is not the set containing 1. That's just 1. That is not the set containing 1. It's 2. That is not the set containing 1. It's 3.
Right.
So that is nowhere in this set. 1 is not in this set. This set has the set containing 1, the set containing 2, and 3. It doesn't have just a 1 in there. Make sense? So the set containing 1 is a very different mathematical object than just 1. Those are 2 very different things.
That's it.
This is the set containing 1. That's just a 1. 1 is not in this set. That's not 1, that's not 1, that's not 1. 3 is in the set. The set containing 1's in the set. The set containing 2's in the set. And 3's in the set. Those are all the things in this set. So that's what we mean by is a member of. You are likely to mix up is a member of with subset. So subset is a relation between 2 sets. Takes a set A and a set B. And what does it mean for A to be a subset of B? It means if X is in A, then X is in B. It means everything that's in A is also in B.
Subset means?
That's what subset means. It means if X is in A, then X is in B. Everything in A is in B. Pictorially, if this is B, then A as a subset means it's contained inside of B. Examples. The set containing 1 is a subset of the set containing 1, 2, and 3. Everything that's in here is in here. The set containing 1, 2, 3 is a subset of the set containing 1, 2, 3. Everything that's in here is in here. The set containing the set containing 1 is a subset of the set containing 1 and the set containing 2 and 3.
Wait, I thought.
This is a subset of this.
What does that little sign mean?
That's the subset symbol.
Subset, right? I thought you said everything is subset.
Everything in this set on the left is in the set on the right.
Sure, it's wrong. Double bracket.
This object right here is also in this set. It's right here.
Right.
Good? All right.
Wait. What's the difference between a member of and a set containing and a subset?
A subset is everything in that.
The set, so 1 is in this set.
Yes.
Look at here versus here. 1 is in this set. 1 is not a subset of this set. This set containing 1 is a subset of the set. 1 is in the set. The set containing 1 is a subset of the set. Everything that's in here is in here. It is not true that the set containing 1 is inside this set. This is not in here. None of those are the set containing 1. It happens to be in the set over here, okay, but it's not in here. So it's easy to get those two things mixed up. One is a member of, the other one is a subset of. So A is a subset of B means that if it's in A, then it's in B. Everything in A is also in B. All right, what does it mean for two sets to be equal? It means that they're subsets of each other. If everything that's in A is also in B, and everything that's in B is also in A, then the sets are equal. Make sense?
Yes.
And then we have the notion of a proper subset. A is a proper subset of B. That means that A is a subset of B, and A is not equal to B.
Okay,
So the set containing 1, this is a prop set of the set containing 1, 2, and 3. But the set containing 1, 2, 3 is not a proper subset of the set containing 1, 2, 3. It's a subset, it's not a proper subset, because they're equal. Can't be equal for it to be a proper subset. It's kind of like less than or equals versus less than. Less than or equals is kind of like subset. They can be the same. Less than means they can't be the same. This is like proper subset.
right.
So usually the line underneath means also include the case where they're the same.
I just like to put on.
Correct. Okay. Common sets. We're going to use these symbols a lot, so you've got to get used to them. First one is the empty set. It's just a circle with a line through it. Circle with a line through it, that's a set containing nothing. Nothing's in the set, it's the empty set. Then we have this n here. So the way I draw it is an n with an extra line like that. That's the natural numbers. That's short for the set containing 0, 1, 2, 3, 4, 5, dot, 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 dot. All the naturals. Then we have the z. Draw z with an extra line. That's for the integers. So, dot, 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 -3, -2, -1, 0, 1, 2, 3, dot, dot, dot. All the positive and negative full numbers.
N is natural set? Or just natural?
N is the naturals. Or you can say the set of all natural numbers, but we just call it the naturals. The same way that z is a set of all integers, or we just call it the integers. And then we have rationals with the q. I don't know why they do on that side. The way I'm used to it is a q with an extra line over here. And that's for the rationals. The rationals are all the possible fractions of integers you can construct.
Like 1/16.
1/16 would be in here. An example of something that's not in here, pi halves. That would not be in there because pi is not an integer. So the rational is all the fractions you can make where it's an integer over an integer.
So that would be real slow, right?
Yes, this would be a real, but it's not a rational. And now what are the reals? The reals are pretty much any number you can think of. If you don't know what a complex number is, then any number you think of is a real number. And I know it looks the way it does there. Typically the way we write that is we do r with an extra line to the left. But some people make their own fonts. Okay. Notice that the empty set is a subset of the naturals. Everything that's in here is in here. It vacuously satisfies the condition. Everything that's in this set is also in this set. You can't find anything in here that's not also in here. Everything in here is in here.
Because that's infinite amount of numbers in an empty set.
No, there's nothing in here. So everything in here is also in here. Right? Okay. Everything that's in here is also in here. So the empty set is a subset of the naturals. And every natural number is also an integer. So the naturals are a subset of the integers. And every integer is also a rational. You can just rewrite it as over 1. 3 over 1, 2 over 1, 1 over 1, 0 over 1. Same number. So every integer is also a rational. So the integers are a subset of the rationals. And every rational is also a real. So the rationals are a subset of the reals. So notice that they're all subsets in that line. Okay, set builder notation. So set builder notation is how we construct a set of things that we're interested in. The way we do it is we write some dummy variable, colon, and then some condition relating to that dummy variable. Or to use slightly more precise language, now you guys know what predicates are, we do a dummy variable and then a predicate in terms of that dummy variable. Remember, a predicate is something where you give it a term and it spits out true or false. So something where, give it the dummy variable, if it spits out true, we include the dummy variable in the set. If it spits out false, we don't include the dummy variable in the set. So now writing that out, here's an example. It's going to be all the x such that p of x is true, such that x makes this predicate true. Let's do a concrete example. Say we want to talk about the set of all tall people. Pick some dummy variable, like x, doesn't matter what dummy variable you choose. Tall people, that's a set of all people x, such that x is a person and x is over 6 feet tall. So it's a set of all x, such that x is a person and x is over 6 feet tall. Notice that this is a predicate in terms of x. This is a person and is over 6 feet tall predicate. So here's how we can represent the set of all tall people. We could also write the set of all the even integers, the set of all evens. What's the set of all evens? Set of all, pick some dummy variable, n. Set of all n, such that n is an integer and n is divisible by 2. That's your evens. Notice this is a predicate in terms of n and some dummy variable n. Another way we could have written the rationals. The rationals, they're the set of all y over x, where y is an integer and x is an integer and x is not equal to 0. Because you can't divide by 0, right? So there's all your rationals. Or we can think about a parabola. What's a parabola? It's a set of all points, x comma y. So don't think your dummy variable has to be just an x. So now my dummy variable is an order pair, x comma y. So what's a parabola? It's a set of all points, x comma y, where x is a real number, y is a real number, and y is equal to x squared. And so that gives you these points on the plane, if we were to pick all those points. It gives you that parabola. Right? We could pick 0, 0. We could have picked x over here to be 1, then y would have been 1. If we would have picked x to be 1/2, then y would have been 1/4. And we would plot this parabola. If we picked every possible real number x, got the corresponding y that satisfied this, that would give us all the points on a parabola. Okay, so there's some examples building up some sets using this set builder notation. We're going to use set builder notation a lot, so good to get comfortable with it. Now let's define some set operations. Unioning of two sets. So here's some set A, here's some set B. Maybe they overlap, maybe they don't.
So the U is a union?
That U is the union symbol. A union B. What does the union mean? It means we want to include all the points in either of the sets. That's a union. More precisely, what is A union B? It's equal to the set of all x, where x is in A or x is in B. If x is in A or x is in B, we want to include it in the union. Notice now this is a set operation. Before, we were talking about set relations. When I say A is a subset of B, that's something that we can either call true or false. When I say this is a subset of this, we can call this true or false. Now we're talking about set operations. A union B, true or false? It doesn't make sense. It's a set operation. It takes two sets and it spits out a set. Looking back at the numbers, here's a relation on the numbers we all know and love. 1's less than or equal to 2. You can call that true or false. But 1 plus 2, we can't call that true or false. It's not a relation. It's an operation. It takes two numbers and spits out a number.
Right.
So we're talking about set operations. These take sets and spit out sets. Okay. So we're defining the set that they spit out. So A union B, that's a set of all x where x is in A or x is in B. A intersect B, the intersection now is just this portion of it right here. Which points are those? Which points are in the intersection?
Just points.
Are the points in the intersection in A?
Yeah, they're A and B.
They're the points that are both in A and in B. So A intersect B is a set of all points x where x is in A and x is in B. So the union is an or. The union is like the or in sets, and the intersect is like the and in sets. Okay.
What you're saying is group A holds 1, 2, 3, and group B holds 2, 3, 4. The intersect would include 2, 3.
Yes.
Good.
The intersection. Yes. 2, 3. If I remember what you said right. Okay. Next. Set difference. So I have the set, here's A, here's B. So I start with the set A and I subtract set B. So I have A, now I remove all the elements that are in B. So I start with A and I get rid of all the elements in B, and that leaves me with the pieces over here. That's A minus B. Pictorially. So that's a set of all x where x is in A and x is not in B. That's what we mean by set A minus B. Start with set A, remove all the elements in B, and what are you left with? You're left with just these elements.
You don't minus the whole thing.
But you can't minus something over here because that wasn't in the set. How do I subtract this point from this set?
So I take this set, minus this.
That's what we just did. We took this set and we minus this set. They happen to have some elements in common. We removed all the elements they had in common. Essentially, we got rid of the intersection. All right, more concrete. A is a set 1, 2, 3, 4, 5. Now I tell you to subtract 5, 6, 7, and 8. Take this set, now remove all those elements. What are you left with?
1, 2, 4.
The set 1, 2, 3, 4. I say, here's A, all the points in the plane inside of A. Here's B, all these points. Now I say do A subtract B. Start with A and get rid of all B. What are you left with? You're left with all the points on over here. Okay.
You just get rid of B. Everything in B, you just take.
Notice A minus B is very different from B minus A. If I would have done this set minus this set, what would I have been left with? The set containing 6, 7, and 8. If I did this and I subtracted this away, then I would have had the set containing 6, 7, and 8, which is very different from this minus this. Similarly, if I would have done B minus A, that would have left me all the points over here. That would have left me these points, right? So that's what we mean by A minus B. That's a set of all x where x is in A and x is not in B. We do this minus this, that's everything that's in here, that's not in here. Okay. Finally, the cross product between two sets. A cross B. A cross B is a set of all ordered pairs x, y, where x comes from A and y comes from B.
X. Cross, not times.
Cross. We don't want to say times because we don't want you to think that this is the operation on the numbers. So typically they say cross or cross product. They might sometimes say times, but
Okay.
usually from context you can understand.
Not actually in the number in the set, you're just set.
Right, so let's go through examples of each of these. We're going to have A be the set 1, 2, 3, B be the set 3, 4, 5. So A union B then, 1, 2, 3 union 3, 4, 5, is a set containing 1, 2, 3, 4, 5. It's everything that's in here or in here.
Right.
A intersect B is
So
just a
it's
set
not-
containing
it's
3.
not 1, 2, 3, 3, 4, 5.
Sure it is.
Yeah, that's true. They're identical.
Yeah, listing an element multiple times doesn't change anything. This set intersect this set is everything that's in both, the set containing 3. A minus B, so we start with this and we remove everything in here and we're left with 1, 2. B minus A, we start with this, subtract everything that's in here, we're left with 4, 5. Now A cross B is a set of all the ordered pairs we can create where our left-hand element comes from A and our right-hand element comes from B.
So B cross A would be the exact opposite. It would be 3,
It would be
1.
flip all these around. Right. So A cross B, we have 1 paired with 3, 1 paired with 4, 1 paired with 5. Then we have 2 paired with 3, 2 paired with 4, 2 paired with 5. Then we have 3 paired with 3, 3 paired with 4, 3 paired with 5. There's A cross B. So those are our basic set operations. Some properties on sets. Union. A union B is the same thing as B union A, and A intersect B is equal to the same thing as B intersect A.
Right.
So, the way we talk about that property, when operation has this property, we say that the operation is commutative. You know that addition is commutative on the real numbers. You know that multiplication is commutative on the real numbers. You know that subtraction is not commutative on the real numbers. 7 minus 3 is very different from 3 minus 7. So these two operations are commutative. How could we prove that they're commutative? Let's do a quick scratch work of a proof. A union B, by definition, is equal to the set of all x, such that x is in A or x is in B. You with me? Now, side proof really quick. We'd have to prove this first. I really quick need to prove to you that alpha or beta is logically equivalent with beta or alpha. I know this is a bit tedious, but I want to do it full blown the first time.
We have to do that.
You'll get comfortable with what level of proving you have to do. Anyways, so if we have true, true, then true or true is?
True.
True. True or false is?
True.
False or true?
True.
False or false?
False.
True or true?
True.
True or false?
True.
Or sorry, that would be false or true. This one's true or false,
True.
and false or false.
False.
And you see, okay, they're the same thing. So notice that this right here, x and a, that's a proposition. That's something that's either true or false. Well, strictly speaking, it's a predicate. So this is something that's going to be true or false. This is something that's going to be true or false, and we're ORing them together. So we just barely showed that this is identical to x in B or x in A. Right? We just barely showed that alpha or beta is identical with beta or alpha. We can swap the order. So here we proved OR is commutative. We just proved it. Doesn't matter what order you OR things together.
Right.
And so we can just barely use the fact that OR is commutative. Right? And now, by definition, what is this? This is the exact definition of B union A. B union A is a set of all x where x is in B or x is in A. So that's a quick scratch proof of how A union B is equal to B union A. And we could do a similar thing to prove that A intersect B is equal to B intersect A. If we switch this with an intersect, that just turns this into an and, this into an and this into an intersect. And we'd have to do a quick truth table to prove that and is in fact commutative. And it turns out it is. It doesn't matter what order you and things together. Alpha and beta is the same thing as beta and alpha. Make sense?
Yes.
So the way we would prove these things is we reduce them down to their exact logical definition. Notice that we use logical notation in defining each of these operations. And then we can use the properties we know about logic to then discover our properties about sets. And most of the time you can pretty much guess that it's true, or it's just going to appeal to your intuition. But I want you to understand how you can reduce it to its precise definition and then use the rules of logic that we can precisely show with the truth table. So you can prove this every little step of the way. All right, this next property is called associativity. If you take A and B and union them together, and then you union them with C, you get the exact same thing as if you union B and C together first, and then you union it with A. And this would use the fact that OR is commutative. When I have alpha or beta or gamma, it doesn't matter if I OR those together, then OR that, or if I OR those together and then I OR it with that. Gives me the same thing. So we'd prove that with a truth table, and then that is what we would ultimately use to prove this is the case. And similarly with AND. Show that if you put the parentheses there, it's identical to if you put the parentheses there, we'd prove that with a truth table. And now we'd use that truth table to prove it here.
It's also the same thing as put parentheses around all three.
Strictly speaking, an operation takes two terms at a time. So if we were being completely rigorous, this right here doesn't make sense. I have to have either parentheses here, or I have to have them here. I have to specify which two I'm applying it to. Because now, alpha and beta, this is just going to be true or false. So now it's something that's true or false and something that's true or false. Okay, now we know it. So, strictly speaking, this is nonsense notation. Of course, we're never that strict when we write out all this stuff. We usually expect the reader to understand that it's associative, and so it doesn't really matter where I put the parentheses. That's what associativity essentially means. Put the parentheses however you want. All right, next. If I take a set and I union it with the empty set, what do I get? If I take the set 1, 2, 3, and I union it together with the empty set, what do I get?
1, 2, 3.
You get the set containing 1, 2, 3. Take everything that's in here or in here, and what are you left with? Just the things that were in here. So unioning with the empty set does nothing. So A union the empty set is A. This is a lot like how plus 0 works. A plus 0 is just A. A union the empty set is just A. Similarly, A intersect the empty set is kind of like multiplying with 0. If I intersect these two things, what's everything that's in both of those sets? Nothing. Nothing is in both those sets. So if I take the set of everything that's in both of them, I have the set of nothing.
So if you try to intersect, say 1, 2, 3, and 4, 5, 6, the answer would be nothing.
Your answer would still also be nothing. Okay. But any set intersecting the empty set is always just the empty set. Good? Okay. Next one. A union B intersect C is the same thing as A union B intersect A union C. Let's draw this one out pictorially really quick. Okay. So we're doing B intersect C, and then we're unioning that with A. So let's see, B intersect C, that's this circle right here. Right? And then we union it with A, which means now include everything that's in A. So that gives us these points. Everything that's in A or in that intersection. Okay, so that's A union B intersect C. Now let's look at these two. We're looking at A intersect B union together with A intersect C. Hold on. What did I do wrong? Do I have that right? Yes, I do. Okay, sorry. A union, I kept looking down. A union B. That's everything that's in A or B. And A union C is everything that's in A or C. So take everything that's in A or B and in A or C, what do we get? We get all of A both times, that's for sure. Either way, we get all of A, right?
Right.
And then we also get this intersection piece. Everything that's in A or B and in A or C. Then we get the parts that are in both B and C. This intersection. Good? You guys getting tired?
Yes.
A lot of homework to check?
Just stayed up.
There you go.
All right. Let's get a pictorial representation of this one really quick. We won't worry about the crossing ones since those won't come up as much. Okay. So B union C, what's that?
That's between B and C.
That's everything that's in B or C.
Right. Just B and C.
We're unioning. So I want everything that's in B or in C. So if a point is in B or it's in C, we include it. Is this point in B or C?
Yes.
Yes.
Yes. What about this point?
Yes.
What about that one?
No.
Yes.
No. Not
Is this one in B or in C?
Yeah.
Oh, yeah. I thought you were just talking about C.
Looking at this one.
Yeah.
B union C. What about that point?
Yeah.
Yes.
What about that one?
Yes.
What about that one?
Yeah.
What about that one?
No.
So we're including all these little sections except for this. You see that?
Yeah.
That is B union C. But now I want to intersect that with A. So now I only want the ones that were also in A. So I get rid of this section, this section, this section, and we're left with these three little pieces.
Right.
Perfect. Now let's come and think about it this way over here. So here I want A intersect B and A intersect C. Let's find those. So A intersect B, we'll do circles for that. A intersect B, which points are those?
It's the middle one, top one, and middle one.
So that gives us this and this.
Yep.
Right?
Yes.
Those two sections. A intersects C, which points are those?
Bottom one and the middle one.
Bottom and middle.
This one and this one, right?
Yes.
Maybe put X's for this. That and that. So both of them include this section, right?
Right.
Now I want to union those together. So I want to take all three of those, and that gives me those three pieces. So they give me the same thing both ways. All right, you want to see full proofs of any of those? Or maybe you want to see a full proof of one that we didn't do?
Yeah.
Which one do you want a proof of?
The one we didn't do.
This one?
Yeah.
Or this one?
Oh, wait.
You said you weren't going to do the process because they don't come up.
Giving you pictorial intuition might do more to confuse than to help.
We do one of them.
Pictorially represent it? Or just prove it? Just prove it. Okay, we'll prove it. Prove this one?
Yeah.
That one. Okay. So let's write out explicitly what this is. So A cross B intersects C. Okay, I have B intersects C there. So I need to do that first. That's what the parentheses mean. Do B intersect C first. What is a precise definition of that? So this is A cross. Now the precise definition of this set.
B and C.
That is a set of all X such that X is in A and X is in B.
No, and B and C.
Oh, thank you. Okay, and I'm going to choose Y for my dummy variable, and you'll understand why here in a second. So this is a set of all Y such that Y is in B
And Y is.
and Y is in C. Right? Maybe it would have been easier to do the outer one first and then come back to the inner one. Sorry. I'm going to do the outer one first and come back to the inner one. I think it's going to be easier to see. So I want A cross this. This is just some set. We can pretend that that's a set D for a second here. But it's just a set cross a set, right? So using our definition of a cross product, this is a set of all X comma Y. such that X is in A and Y is in the other set, which in this case is B intersect C. That's what we mean. So when I have the set A cross B, by definition, let's go back to this definition really quick. When I have A cross B, that's a set of all ordered pairs X, Y, where X is in the first set and Y is in the second set. So here's a set, here's a set. So this set cross this set is equal to the set of all ordered pairs X, Y, where X comes from the first set and Y comes from the second set. You with me?
Yeah.
Now what does it mean for Y to be in B intersect C? That means Y is in B and Y is in C. So this is equal to the set of all X comma Y, where X is in A, and, parenthesis, Y is in B and Y is in C. That's what it means for Y to be in B intersect C. It means Y is in B and Y is in C. That's what it means to be in the intersection.
Yeah.
With me?
Yes.
Okay. Now, how can I say this real quickly? If I do alpha, and it is true or false, then alpha and alpha is going to be
True or false?
If alpha is true, alpha and alpha is true. And if alpha is false, then alpha and alpha is false. False and false is false.
Oh, that's right. It's not false implying false.
Right. Similarly, alpha and alpha and alpha and alpha. If alpha is true, this is
True.
and if alpha is false, this is
False.
So if you already have a term, similarly, I could have said alpha and beta is the same thing as alpha and beta, right? That's essentially what I've said here. An alpha is the same thing as alpha and alpha. Anding another alpha doesn't change the information. If I'm giving you information about this room, and I say, I'm in it, and you're in it, and I'm in it, the second and I'm in it gave you no new information. Doesn't matter. It doesn't change anything. Okay. So here's how I'm going to rewrite this. I'm using the fact that and is associative, which means I can place parentheses however I want. And I'm using the fact that and is commutative, which means I can and in any order I want. So I can change the order and I can change the parentheses. So this is xy such that x is in A and y is in B. And parentheses, so that's those two. And now I'm going to write x is in A again. Doesn't change anything to restate x is in A, right? And y is in C. So I didn't change anything. I'm still saying the exact same thing I was saying before. Right?
Yes.
So now this is equal to the set of all xy such that x is in A and y is in B, and x is in A and y is in C. Maybe I can skip right to it. X is in A and y is in B is exactly what we mean by A cross B. And is our intersection. X is in A and y is in C is exactly what we mean by A cross C. So A cross B intersect C is the same thing as A cross B intersected with A cross C. And if we did the or, if we did this one, sorry, we got rid of it. If we did this proof, where we did union instead, the only thing that changes is replacing all of our ands with ors here. Oh no, this is still an and. That one's still an and, but this becomes a union. Not still an and, but this one becomes an or. Similarly, if you know alpha, you can also or alpha with it, and it doesn't change anything. Alpha is the same thing as alpha or alpha. Right?
Yeah.
So if you know alpha is true, you already know alpha or alpha is true. So going from here to here, oh no, we're still anding, so forget that. This is just a distributive. Maybe we should just write the truth table for this. So going from this step to this step, I'm going to write the truth table. Alpha and beta or gamma is what we're looking at. The truth table for that. How do you distribute an and over an or? You do. It becomes alpha and beta or alpha and gamma. So let's prove this really quick. We're going to try and do a bunch of the algebra in our head as we go. So alpha, beta, gamma. How many different combinations can we have? If we have 3 variables?
True, false, true.
True, true.
How many different combinations can we have?
9.
8. This has 2 options, and for each of its 2 options, we have 2 options here, which gives us 4 options. And for each of those 4 options, we have 2 options here, which gives us 8. So we can have true, 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 false, true, false, true, true, false, 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 true, true, false, true, false, 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 true, false, 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 right?
Yes.
We got them all? Yes. All right, so now let's just examine it. True and true, true and true or true is?
True.
True. And when they're all true, this is obviously true as well, right? Okay, so let's look at this one. So gamma is false, but the other ones are true. So we have true or false is? True. True and true is? True. All right. So true and true is?
True.
True and false is?
False.
False. False or sorry, true or false is?
True.
True. Okay? This time beta is false. So false or true is?
True.
True. True and true is?
True.
True. True and false is?
False. False.
False. True and true is?
True.
False or true is?
True.
Next is, so only alpha is true, the other ones are false. All right. False or false is? True and false is? True and false is?
False. False.
True and false is?
False.
False or false is?
False.
All right. Now only alpha is false, the other ones are true. True or true is?
True.
False and true is? False.
False.
False and anything is false. False and true is?
False. False.
False and true is?
False.
False or false is?
False.
Next. Only beta is true. Well, notice how if alpha is false, the whole thing's false, right? If alpha is false, doesn't matter, the whole thing's false. Similarly, if alpha is false, this piece has to be false. False and anything is false. False and anything is false. So false or false is always false. So anytime alpha is false, the whole thing's false. See that?
Yeah.
And then, ta-da, they give identical things. So this is a valid rule of logic. Alpha and beta or gamma is the same thing as alpha and beta or alpha and gamma. Okay, that's what we're using here. Alpha and beta or gamma is the same thing as alpha and beta or alpha and gamma. And then finally, that's exactly what it means by the union. So x in A and y in B is the same thing as x in A, or the point x, y, and A cross B, or x and a, y, and c is the same thing as a cross c. So that's how you prove this one. All right, so that's pretty much it for naive set theory, everything that we're going to cover. And so next week we will be starting geometry proper. And we will be starting with the axioms of geometry and proving things with the axioms of geometry. So before we do that, let me give you a taste of how this used to be done. Let's pretend that we are back to Euclid's elements and we're doing Euclid's geometry. Euclid's geometry is a lot more fast and loose than the geometry that we're going to be doing. We're going to be doing a much more straight, much more rigid, much more precise geometry. But I just want to give you a feel for how these proof things are used. So going back to Euclid, his 5 postulates. Postulate 1 was that 2 points define a line segment. So postulate 1 was if I have A and I have B, that gives me that I have the line segment AB. 2 points define a line segment. If I have 2 points, I can get a line segment out of it. Number 2 is you can extend any line segment indefinitely. So if I've got some line segment, I can make it longer. And I can make it as long as I want. If you have a line segment, you can make it longer. The third postulate is that if I have a point, we'll call it point O, and then some line segment, and some line segment, but some line segment at the point. So if I have a point and some line segment at the point, then that gives me a circle. That defines a circle with that radius.
Is the radius the entire width of the circle? Or the
That's
center
the
to
radius.
edge?
Center to the edge. Diameter.
Distance from the center to the edge.
We looked it up.
4 is that all right angles are congruent. We won't be using this today. And then Euclid's 5th, I'm not going to give it to you how he has it, but it's logically equivalent to if I have a line and I have a point not on the line, then there is only one line I can draw through the given point such that these 2 lines don't intersect. Which makes those lines parallel. But these are his 5 postulates. These are the only things he assumes. Now you'll notice that you're allowed in geometry, when you're doing Euclid's geometry, to use a compass and a straight edge. The straight edge enables you to do this. If you have a straight edge, and I have 2 points, you know what a straight edge is. It's like a ruler, but no measurements. Just like this yardstick, here's a straight edge. Notice that if I have 2 points, I can use this straight edge to connect them. So anytime I do this, logically, I'm using postulate 1. So the tools are just a way of using your postulates. Postulate 2 says, okay, I take my straight edge. Maybe my straight edge was only this long, so I need to move it down a little bit to extend my line segment. Is that legal to do? Yes, according to postulate 2. And then a compass, you know what a compass looks like, right? Helps you draw a circle. So if I take my compass, so if I have this point and this point, so this line segment here, and I take my compass, I can use that to draw my circle. So that's what postulate 3 is doing. It's telling you you can use a compass. So 1 and 2 say you can use a straight edge. 3 says you can use a compass. And then these 2 are just telling you other properties. But that's why when you see people doing geometry, Euclidean geometry, they're often using a compass and a straight edge. Because they're really using these postulates. And so it's a very pictorial way to do geometry, which is what's so nice about it. Its imprecision is what's bad about it, but the fact that it's so pictorial in nature is what's great about it. So then Euclid's first theorem is that there is an equilateral triangle. So that's the first thing that we're going to prove. I'm going to prove that there's an equilateral triangle. How do we do that? Well, we start by taking some line segment. Oh, I think it's given a line segment. Sorry, here's what I think it is. I think it's given a line segment. There exists an equilateral triangle with that as its length of the sides. Right? Okay, so with a compass and a straight edge, if I want to prove that a right triangle exists, I need to construct it. How do I do that? I would take my compass here and start drawing a circle over here. So start drawing a circle around this point using this as my radius. You with me?
Yeah.
Now, come over here and start drawing a circle using this as my radius. And those two circles are going to intersect at a point. Now, since this segment, call this point C. Now notice that AC has to be congruent to AB. How do I know? Because they're both radiuses of the same circle. Similarly, I know CB, this line, CB, has to be congruent to line segment AB. How do I know that? Because they're both radiuses of this circle centered over here. So now I know that AC is congruent to AB is congruent to CB. So all the side lengths are the same. This side length is the same big as that side length is the same big as that side length. So it is an equilateral triangle, equal-sided triangle. So that's pictorially. I didn't write down all the verbiage for the proofs. We'll get a lot more into that. I just want you to see some of the pictorial nature of all this. And so that's how you go about doing these proofs. They're very pictorial in nature, and every time you use something, it makes reference to your postulates over here. So this is the way that Euclidean geometry was developed. Unfortunately, ours doesn't get to be that pictorial, but we'll get to the point where if you can draw the picture for it, you can pretty much figure out the logic for it. So we'll still be doing similar things where your job is, I got to figure out how to construct this using a ruler and a straight edge. Or sorry, using a compass and a straight edge. And if you can do it, there's going to be corresponding pieces of logic you can go back to and say, oh, that's what I plug into my proof. I don't know. Should we try a second proof? So his second proof now is given a line and a point not on the line. I don't remember how to do these off the top of my head, so hopefully we don't get stuck. I remember that this one took me a second to figure out. So if we have a line segment and a point not on the line, it is possible for me to draw a line segment at this point, draw some line segment at this point, such that this line is the same long as this line. That's my goal. So all I start out with is this, and now I need to figure out using a compass and a straight edge how I can create a line segment along here as long as right here. Now you might be tempted to say, just take that with your compass and then go draw out the point and fill it in. But your compass doesn't have memory. You can't assume your compass has memory. Our modern compasses are built with so that it stays rigid. But the compasses that the Greeks were thinking about when they said this, they're not rigid. They don't stay rigid. So how do you know that your compass doesn't change when you pick it up and move it? So I can't do that. So that's our goal. Our job is to construct a line segment this long at this point. Okay, so how on earth am I going to do that? I'm not sure for a second. I have to play with it. First off, I know I can construct an equilateral triangle. Call that point D, so that these are the same. That's using my first postulate. And then let's see. If I did a circle, maybe get those points collinear. Might be dangerous to try and do this on the fly. I know I can connect that. I can mark B out the same distance here. I could find a point on here, C or D, so that this is the same big as that if I want. Extend this like that. I end up using it. I shouldn't try to do this on the fly. I think I'm in confusion more than I'm going to help you. Sorry. Let's do an easy one that I know I can do on the fly. Another one of his postulates is that given a line segment, you can construct a square with that as its side. So this is point A, B. My job now is to come up with a square with that as its side length. Okay, so let's do that one really quick. So first off, I know I can extend that line, right? Come here, draw a circle. Call this point C. So I know that this distance is the same big as that distance. Do I care about that? Okay, yes I do. And then erase that circle once we have that point. So now come here and just pick a circle of any radius as long as it gets you past the point A. So I can do a radius clear out to this point. So I'm drawing a circle with that as its radius. Now come here and draw a circle with the same radius like this. Where these points intersect has to be the same distance from here as it is from here, because those are both circles with the same radius. So this distance has to be the same as this distance, which means that this point is lined up with this point. Or in other words, that's a right angle. And now I can come back to this circle and I can draw up to where that intersects here. Now it gives me that side. So now I got this side of my square, I got that side of my square. I can repeat the same process to get this side of my square, and then connect the points to get my full square. So that's how you show a square exists. Anyways, I was really tempted to use just his elements to do this class. We're not going to do that. We're going to be using more precise axioms. We're going to be using Hilbert's axioms. So next week we'll be starting geometry proper. We'll be starting chapter 3 where we go over the actual axioms and start proving things, and we'll start rigorous proofs. Any questions for any of that? Before I put you all to sleep? It's okay. Requires a lot of thinking. It mentally exhausts you. They tell me when you teach high school kids, you should only lecture for 30 minutes at a time because they can't handle more than that. I say that's dumb. Keep pushing them until they can handle 3 hours. You don't mollycoddle the fact that they can't pay attention. You try and force them to.
So homework is 15, and then the review, and then how does the test work?
Oh, is there a test after that?
No.
Let's see. Our first test is on chapters 2 through 5.
You kind of tell us how you do 15.
How you do 15?
215. In each problem below, you are given certain statements which we shall follow through. Then a theorem is stated. In some cases, the theorem may be false. Others, it may not be enough information given to decide whether the theorem is true or false. Write out proofs. We refer to our given true statements in each problem as false.
So exercise group 215. Okay. And let me pull up my solutions. Oh, this is in full. That's why. Okay. 215. So this is the first time you're introduced to proofs. Maybe I should give you guys the solutions on this one and let you figure it out. Oh, yes. That probably helped, huh? So, hypothesis is the information that we're taking for granted, and we're trying to show that the hypothesis implies a conclusion.
Right.
Or the theorem, in other words. Yeah. So I'm trying to use the fact, so let's assume it's true that Uncle George will take us skating today if Mother says we may go. We'll assume that's true. We'll also assume it's true that Mother has said we may go. Now I'm going to try and prove that Uncle George will take us skating today. So let's see what a proof like that looks like. Oops. Shoot. Okay. So, proof that Uncle George will take us skating today. 1. Mother says we may go implies Uncle George will take us skating today. That was the first statement of our hypothesis. Right?
Okay.
Just writing out the logic for you. What implies what? 2. Mother says we may go. Hypothesis 2. So I know alpha implies beta, and I know alpha. Therefore, Uncle George will take us skating today. That's combining statements 1 and 2.
That's how we write it out.
This is a perfectly valid way to write it out. So here I show you explicitly, this implies this. Look, we have this, therefore we have this. Looking at the next one. There's no animal life on the moon. One of our premises was, if there's no oxygen on the moon, then there's no animal life. Or in other words, there's no oxygen on the moon implies there's no animal life on the moon. The second statement given to us in our hypothesis is that there is no oxygen on the moon. Therefore, conclusion, there is no animal life on the moon. And just combining those two statements together.
Okay, that's hypothesis one.
A little smaller.
You have to say that that's hypothesis.
Initially, yes. Let's be very clear about where you're getting each piece of information. All right, let's look at number 3. People with green eyes cannot be trusted. Joan has green eyes, therefore, Joan cannot be trusted. Now, my proof, I put a note in here. Strictly speaking, there's not enough information. Because Joan may not be a person, she could be the name of a cat. We'll assume it's a person and continue from there. All right. So proof that Joan is a person who cannot be trusted. So I threw that in as part of the statement. That's why I threw it in.
Say that strictly speaking. Or will
No,
we
this is me
describe-
making a note for you. In
But
case
you
you were
can't-
overthinking it.
You can't totally prove Joan's a person.
It didn't say anything about here Joan being a person. So I'm basically saying from here on out, I may assume that we know Joan's a person. Okay.
Prove it.
Yeah, for the sake of the proof. So here's what I'm going to prove. Joan is a person who cannot be trusted.
Okay.
Not sure what that's supposed to be anyone. Anyone being a person with green eyes implies they are a person who cannot be trusted.
So we said any person with green eyes cannot be trusted.
I want to write it down with the implication arrow in there. I want to show you explicitly alpha implies beta. That's what I'm trying to show you. You see that? Similarly, Joan being a person with green eyes implies Joan is a person who cannot be trusted. I'm plugging Joan into here. Our hypothesis is that anyone who has green eyes can't be trusted. Now I'm plugging Joan in as a person. So this is just rephrasing statement 1, plugging in Joan. Make sense? Now, the second part of my hypothesis is, I don't know why I wrote that so weird. Joan is a person with green eyes. So she satisfies the antecedent here.
Yeah.
So this is alpha implies beta. We know alpha is true. Therefore, we know beta is true.
Why does it say Joan being a person with green eyes?
What?
Number 3 is the same thing as person number 2 does.
That's the point.
He's just saying
This
alpha
says alpha implies beta. This says alpha. This right here says if Joan is a person with green eyes, then she's a person who can't be trusted. This says Joan is in fact a person with green eyes.
Okay, right. Joan being a person with green eyes implies she can't be trusted. Joan, it does have green eyes.
Exactly. This says alpha implies
Joan
beta.
cannot be trusted.
Right. If you went back to I said our most basic way that we're going to prove things, we're going to combine two things. We're going to take if we know that alpha is true and we know that alpha implies beta is true, then we must know beta is true. If this is true and this is true, this has to be true.
Not necessarily.
Yes. If alpha is true and alpha implies beta is true, beta has to be true. So, we know alpha implies beta, and we know alpha. Therefore, we know beta. It's the most basic logic that you use in proofs. You know alpha implies beta, therefore you know beta.
That's what we know. Hypothesis 1, hypothesis 2, combined statement.
That's the general layout.
Wait, what about a statement?
Let's look at one that's a bit more complex. Let's look at 8. So 8 says, x plus y equals 20, x minus y equals 4, therefore x is not equal to 11. You with me?
Yeah.
So let's look at that one. So proof x is not 11. All right, x minus y is equal to 4. That's hypothesis 2. X is equal to y plus 4. I took this, and what did I do? I added y to both sides.
Yeah.
X minus y plus y gives me just x. 4 plus y gives me y plus 4, same thing. So this is just arithmetic on line 1. Okay? Now, x plus y equals 20. This is hypothesis 1. These were our two hypotheses. So I know x plus y equals 20. But up here from statement 2, I know x is equal to y plus 4. So I can replace that x using the second law of identity. Equals, maybe substitute for equals. X plus y is equal to 20. Or in other words, I substituted 2 into 3. Statement 2 into 3. Okay. Now, we're just doing some arithmetic. X plus 4 plus y equals 20 is the same thing as 2y plus 4 equals 20. Just doing the arithmetic. Just bring the two y's together. 2y plus 4. Still equal to 20, right?
Yes.
Subtract 4 from both sides. We get 2y is equal to 16.
Y.
Divide both sides by 2, we get y equals 8. So that's just doing a bunch of arithmetic on line 4. Okay. Now, looking back up here, x plus y equals 20, y equals 8. I can substitute that in for the y. So x is equal to y plus 4. That's substituting 5 into 2. Which gives me that x is equal to 12, which is not equal to 11. So x is not equal to 11.
Okay.
So there's a more full-blown proof showing you all the steps, trying to make sure you follow piece by piece. This is roughly what I'm after from you in the beginning. A general rule of thumb is write your proof so that the person next to you could understand every single step you took. So you think about him. And if you think my going from here to here might have confused him, add whatever information you need to make that clear, or maybe break it out into another step. So that's my goal when I write this out. I'm trying to write so I think one of you could have understood each one of my steps. That's how much you need to explain it. There'll come a point where you'll all get more comfortable with proofs. We'll be less strict about what you have to do in the proofs. We'll be more lax. That'll be fine. But for now, try and make it very clear. So, there's 15 questions. And then you have the review exercise.
Oh, there's 20.
Oh, did I just not finish?
There's 20, but the last ones are extras.
Oh, the last ones are extra credit ones.
Reach not those.
You can do them. Never think that that I'm trying to pressure you into skipping them. Don't feel that way. Okay, so then you'll have the review exercises after that, which is 21 of those. And then you'll have the algebra review. Don't miss this algebra review, which is 12 of those. The algebra review here is crucial. And we'll spend some time going over that. I was hoping to go over it today, but we ran out of time. So don't skip the algebra review. Make sure you can understand the algebra review. It's trying to give you just a very minimal taste of an axiomatic system.
Oh, wow. And the algebra review, you have to prove all these things.
Right, the algebra review is proving all these things, and they're saying, look, let's call this axiom 1, let's call this axiom 2, and just using these two as axioms, let's prove everything else. That's what it's trying to get you to do. So you're going to assume only two things. You're assuming that you can subtract the same thing from both sides. That's one thing you're assuming. The other thing that you're assuming is that you can divide both things by the same side. So you got to ignore everything you know from algebra and only use these two rules. And you need to specify each time you're using one of those rules. Now you're going to get confused because going the other way, so this right here says A plus B equals A plus C implies B is equal to C. So it gives you one way of the implication. You are also going to want to use the fact that B equals to C implies B plus A is equal to C plus A. You're going to want to use this information, doing the implication the other way. You can do that. You can do this one is a theorem of logic. So it doesn't need to be an axiom. You can always do this. So going this way, you can always do for any operation. And we proved this in logic. For any operation, doesn't matter what the operation is, circle. If B equals C, then B circle A is equal to C circle A. How do we prove this? So let's assume B is equal to C. B circle A is always equal to B circle A. This is the first law of identity. Everything is identical with itself. But now using the law of substitution, I can replace a B with a C. So then B circle A is equal to C circle A. Yes. If B is equal to C, then so in other words, B equals to C implies this is true. If this is true, then this is true. For any operation. For circle, for plus, for times, for divide, for whatever it is, as long as it's well defined. So the author only explicitly writes one way of the implication. This being true implies this is true. The other way on the implication we already have from logic. Similarly here, he says if this is the case and this is the case, the other way we already have from logic. So he doesn't need to give us as an axiom, but you can still use that. Make sense? So you're going to probably feel stumped trying to go from here to here. You can do it. You can do it because of logic. You don't need it as an axiom. So here's your two axioms. Everything else you get from logic. And then you're going to just use those four rules, our two rules from logic, the two ways of thinking about from logic, and the two he gives you here to prove all these statements. And so the point here is to break your intuition, stop relying on just operations that you memorized back when you were doing algebra, and actually think about it. And you think about precisely which rule you're using and how that's allowed. Okay? But you can still assume basic arithmetic that you already know and love. You can assume 15 plus 4 is 19. Yeah, you know that. So you can still perform basic arithmetic on numbers. That's okay. Okay.
We can go over that time, go over one algebra review, just so we can add it.
I did a couple of these already at the end of last lecture. But yes, I will do another one. So we're going to prove if x equals 7, then 4x plus 5 is equal to 33. All right, we're proving an if-then statement. The way you prove an implication is you assume the antecedent and show that implies a conclusion. Assume x is equal to 7. 2.
Can't we just go, then let's plug in 7 for x?
How do you know you can do that?
Have to assume x.
Law of identity. We can. Law of identity. Remember, we can use our two laws of identity. You can substitute equals for equals. So then, 4x plus 5 is equal to 4x plus 5. And I would specify in the side, if you're like, how do I know I can just substitute? Maybe specify, this comes from logic. It's not, we didn't need one of our axioms to prove it.
Oh, we're just showing you every step we take.
Show me all the logic of the steps you take. Yes. 3. Then 4x plus 5 is equal to, now I'm going to assume that you can just do arithmetic.
Right.
So 4 times 7 is 28 plus 5, which is equal to 33. 4. Therefore,
And on that line, would you say arithmetic?
yeah,
You have to say arithmetic on line 3 or what?
you can just write arithmetic right there. Make it clear you're not using any other rule. Therefore, 4x plus 5 is equal to 33. And fill in the square there to remind the reader, hey, that's what we were after. We're done. I showed 4x plus 5 is equal to 33.
I take a picture of that.
You sure can. It's also recorded.
Oh,
Whatever you'd like. Okay, any other questions?
The square means done, voila.
The square means, and thus it is demonstrated.
yeah. Okay.
Okay? Don't throw away the homework that we didn't grade today. Just a reminder. Huh? Okay. And I think we're good, right?